So if you look at the photograph on the left in Seoul, you're looking at copper. Of all the metals in the periodic table, copper is the most essential next to iron that we use for steel. And that's because we use copper to generate electricity, we use copper to distribute electricity, we use copper to store electricity. And when we think about electricity, electricity is fundamentally related to economic development. So when we look at the map here, Our World at Night, a compilation from NASA, you can see the haves and have-nots. You can find Seoul, South Korea, and you can see the stark divide of North Korea, which essentially lives in almost a pre-industrial revolution state. When we look at this map, you're looking at copper physically embedded in the infrastructure in every single one of these cities and countries around the world. And you can also see a huge gap when you look at Africa, where we estimate over the next 100 years, the population will grow to as many as 4 billion people. If you look at countries in South Asia, India, Bangladesh, Afghanistan, Pakistan, 100 years from now, demographers tell us that 80% of the world's population will live in Africa and Asia. So when we think about development, we have to think about all of the mineral resources required to develop. If you look at the data here for electricity generation per capita, which essentially is how much electricity does each person use in each of these countries, and you look at the really positive change in South Korea and China over the last several decades, that change is fundamentally the UN Sustainable Development Goals. And when you look at the countries on the bottom right, the DRC and India, the development of those countries, which is directly related to human development, is tied to access to energy by way of access to electricity. Now, in high-income countries, we increasingly are using a lot more electricity for a variety of computational tasks. In order to train a new large language model, that requires the same amount of electricity as binge watching Netflix for 185 years without stopping. We use more electricity mining Bitcoin than the whole country of Bangladesh and all 171 million people just to mine Bitcoin. If we rank data centers globally in terms of they're a country, data centers rank as the 17th largest consumer of electricity in the world. And over the next decade, data centers will consume more electricity than all of India's 1.5 billion people. So for those of us in the room who were born in a high-income country, we have a lot of copper already in our infrastructure that most of us don't really realize is there. So I'm going to show you now a sequence of images where the y-axis is how much copper is physically embedded in the infrastructure of a high-income country on a per-person basis. So over the 100 years from 1900 to 2000, this is how much copper is physically embedded in the plumbing in a high-income country, in the wiring in a high-income country, in all of our domestic equipment in a high-income country, all of our air conditioning and refrigeration in a high-income country, all of our industrial equipment, all of our non-car, non-vehicle forms of transportation, and then bottom right is all our motor vehicles, and the black line is everything else. So for those of you born in the EU, for those of you born in the US or Canada, you were born into a world where for you, just you, there's already 200 kilograms of copper behind the wall. It was just there when you came out of the womb. If we want parity globally, here's how much copper, just copper, we need to develop these regions of the world. We need 1 billion tons of copper for Africa, billion tons. 360 million tons just for India. 121 million tons just for Pakistan. This is the UN Sustainable Development Goals. This is the amount of copper that we need to raise the standard of living in each of these regions to the standard of living that is, for most of us, normal in high-income countries. Now that copper comes out of the ground and some of it is recycled. So we're looking here at the y-axis is millions of tons of copper per year. The x-axis is time. And if we take copper production from mines going back to the year 1900 through today, I'm just showing you the data for the year 2000. We currently have 709 operating copper mines around the world that are producing copper 24 hours a day, 7 days a week, 365 days a year. And this year, those mines will produce about 22 million tons of copper. Now, we also add recycled copper to the total refinery supply, which is about 4.8, or let's round up to 5 million tons. So total supply is about 27 million tons. Now, if you look at the blue line and you go back to 1900, the annual growth rate or the increased consumption of copper essentially tracks global economic growth. So you can use annual consumption of copper and its increase over the last 125 years as a proxy for global economic growth. And then you can simply project how much copper do we need to mine and how much copper do we need to recycle over the next several decades to maintain historic economic growth. The bottom line is the amount of copper we need to mine needs to increase at about 2% per year every year for the next several decades. The top line is the refinery supply, and you'll see the divergence in 2050. This is calculated assuming that we continue to get better at recycling and we recycle more copper, so more recycled copper becomes part of the global supply. And if you look at the projections in the year 2050, what we see is that mined copper is about 65% of the total supply, and recycled copper is about 35% of the total copper supply. Now, those projections are how much copper we need to continue economic growth at historic rates. We've got a problem when it comes to copper. The dotted line here is the amount of copper that all the world's copper mining companies have announced they plan to produce from currently operating copper mines over the next several decades. So that's going in the wrong direction. The top dotted line is the amount of copper that all of the world's copper mining companies could produce if every discovered copper deposit gets put into production over the next couple of decades. And what you see is we need about 37 million tons of copper to come out of the ground to maintain economic growth. We have 30 million tons possible that we could mine. So we've got a 7 million ton shortfall. Now, in terms of the quantity, the y-axis here is the cumulative copper throughout all of human history from the Stone Age through today. And what you see is the projection out to the year 2050. We need to mine between now and 2050 about 800 million tons of copper just to maintain basic business as usual economic growth. 60% of the world's copper comes from porphyry copper deposits. And if you look at a map here, you can see that porphyry copper deposits, they're associated with arcs, with subduction zone environments. And I'm not going to go into these details, but happy to talk with anybody interested in them over the course of the week. We've spent a lot of time developing what is a pretty good understanding of how porphyry copper deposits form. These copper deposits, as I said, supply 60% of global copper. They also supply about 100% of global rhenium, global tellurium, which we need for cadmium telluride solar panels, about 100% of the world's molybdenum. They supply important and relatively substantial amounts of gold and silver. So there's been a lot of effort to understand how porphyry copper deposits form in arc environments. But what I want to spend the rest of my talk doing is trying to convince you of the need to find more of these deposits. We think of them as a needle in the haystack. So if we go from a porphyry deposit here that typically forms within the upper few kilometers of the Earth's crust in a subvolcanic environment, and we look at a cross-section here of a porphyry deposit that has experienced weathering by groundwater over a period of millions to tens of millions of years, What happens after a porphyry copper deposit forms in the near surface environment is that rainwater percolates into the subsurface. It reacts with and dissolves copper sulfides and copper iron sulfides, and it transports that copper from the upper portions of a porphyry deposit to deeper levels of the porphyry deposit. And when it does that, it leaves behind what's called a leach capping or a leached cap. And what we then have happen is the copper that is in solution here, as that groundwater percolates to deeper levels of the Earth's crust, the copper will come out of solution and precipitate, as shown in the blue, in what's called the high enrichment supergene chalcocite blanket, which has the shape of a blanket in 3 dimensions overlying what is still left of the original hypogene copper sulfide deposit beneath. So for thousands of years, this is how we found copper deposits. You can read about copper in the Bible. It's mentioned many times. You can go to parts of China, parts of the Middle East, parts of Northern Europe, and what we see over thousands of years is that we were able to find copper deposits by noticing the minerals that formed during the oxidation of copper sulfides. And these greenish and bluish minerals, they were a telltale sign to humans for thousands of years that those rocks contain anomalous concentrations of copper. General background copper concentrations in the Earth's crust is about 25 to 30 parts per million. And so we were able to find these rocks that might have 1,000 ppm, 5,000 ppm, a weight percent, 2 weight percent, 3 weight percent copper. And this worked really, really well. We figured out that if we send geologists out with Bruntons, put their boots on, take shovels, we could dig into the soils that represent the leached cap, and we could analyze those soils, and we could use their signal from the general background, the noise, as an indication of copper in the subsurface. We figured out that if we look at porphyry copper deposits, there's a lot more magnetite associated with copper-rich porphyry deposits than magnetite in all other igneous, sedimentary, and metamorphic rocks. So we could fly airplanes over the crust, and we could use these magnetic sensors, and we could determine where there's a huge amount of magnetite relative to all of the surrounding rock. We figured out the general shape of mineralization in porphyry deposits, so we can relate the magnetic signal to the potential presence of copper minerals in the subsurface. We then figured out that if we send large electrical currents into the subsurface and we measure how fast or how slow those currents flow through the minerals in the subsurface, we could generate chargeability maps, we could generate resistivity maps, and then we could correlate those with the magnetic maps to, in essence, generate 3-dimensional visions of what the subsurface looks like. Now, when electricity flows through the subsurface, it will move fast through any sulfide mineral. So if there's pyrite in the subsurface, that electricity moves quickly. If there's chalcopyrite in the subsurface, that electricity moves quickly. When you sum all of these data, they can suggest the presence of copper sulfide minerals in the subsurface, but the proof is when you drill into the subsurface. So we would then drill into the subsurface using, in this case, a diamond coring bit that allows us to drill and then to recover cylinders of rock in the subsurface. And when those cylinders of rock are brought back to the surface, we can look at the mineralogy initially with a hand lens. We can scan these now and do X-ray diffraction. We can use SEMs and microprobes. In this case, we're looking at drill core in the center, where all of these white quartz veins, the grayish mineral associated with those quartz veins is chalcocite, Cu2S. That forms the supergene copper blanket in porphyry copper systems. The sample on the right, we're looking at drill core that penetrated beneath a supergene blanket, and we're looking at veins that are enriched in chalcopyrite, which is the predominant copper iron sulfide mineral that mining companies target. This is really expensive. on a per project basis, just one project, one exploration team, by the time you have drilled into the subsurface and recovered rock, you've already pissed away tens of millions of dollars. And roughly 1 out of several hundred of your drilling campaigns will actually result in the discovery of a new porphyry copper deposit. So what we have is we have lots of data that suggest the possible presence of a porphyry copper deposit in the subsurface. And when we drill, most of the drilling results in failures, meaning that all of the data generated by the technologies on the left doesn't help you discover a porphyry copper deposit. This is a chart that shows you on the y-axis the number of copper deposits discovered from 1990 through today. And all I want your eyes to see is the record for exploration teams continues to decline. So what we see globally with companies that explore for in the hopes of finding a porphyry copper deposit is, despite generating all of these data and drilling into the subsurface, what we see is several years in the last decade where there was not a single new significant copper deposit discovered, despite the fact that mining companies are spending a lot more money. So the right axis now is the budget just for copper exploration globally. You can see a big peak in 2014 that corresponded to an increase in price. We now spend about $3.2 billion a year just looking for copper. And if you look at the gray bars, the success rate's getting worse. That's because what we see over the last couple hundred years is this is depth beneath the surface on the y-axis, so 0 would be surface. For a long time, all of the copper deposits we discovered, we literally saw them on the Earth's surface. Now what's happening is those deposits, we found them all. We're having to look in the subsurface in areas where there is no outcrop manifestation of copper minerals. So what worked on the left worked really, really, really well. Took us from the Stone Age to the Copper Age to the Technology Age. Provided the copper for economic development in high-income countries that we need for economic development in low-income and lower middle-income countries. The photograph on the right, that's where we're going to find copper deposits today. And you can't see any evidence of a copper deposit in the photograph on the right. This is from an area in what you might think of as the middle of nowhere, Alaska. But below the surface, below all that glacial till, is one of the world's largest porphyry copper deposits, not yet mined. And we started looking a few years ago, my partners and I, at all of the data that mining companies produce. And what are the data that mining companies don't produce, right? Fundamentally, a porphyry deposit is the signal. So what signals could a porphyry copper deposit give us that mining companies aren't using? Well, what you see in the photograph on the right is water. This is water in Alaska that represents the surface flow of groundwater that has flowed into the subsurface, and it has chemically reacted with copper, iron sulfide, and copper sulfide minerals in a porphyry deposit beneath the surface. So we asked a simple question, which is, do mining companies analyze and use water as an exploration tool? And the answer is yes, but all they do is they analyze for the concentration of copper and other metals. How many ppb copper? How many ppm copper? So what we decided to do was to look at more than just concentration, but to look at metal isotopes, the metal isotopic composition of groundwater, to see if we could figure out whether or not there's a signal from noise. And what we did is we essentially worked with one hypothesis, which is that, as the diagram shows on the right side, if groundwater flows through and chemically reacts with copper sulfide minerals in the subsurface, we should be able to detect that chemical signal in the water that has chemically reacted with sulfides. Versus on the left, if groundwater is just flowing through barren rock, there's no signal to measure. So we did a lot of experiments in the lab. We took all of the copper-bearing materials on the left side of the screen. We did simple experiments where we reacted them with water, And then we measured the stable isotope composition of the residual sulfide after chemical weathering and the solution after it had chemically weathered with the sulfide. And we measure copper isotopes, iron isotopes, tin isotopes, moly, lead, zinc, titanium, you name it. If it's in the periodic table and it's got multiple stable isotopes as a metal, we measured everything to see what matrix we might be able to come up with to identify signal from noise. Shown here are the results from one of these experiments, where the y-axis, the delta 65 copper, is the ratio of copper 65 heavy over copper 63 light. The gray bar shows you the initial delta 65 copper value for a sulfide mineral, and after putting that into an experimental apparatus, what you can see is that the water becomes isotopically heavy and the residual sulfide becomes isotopically light. And the reason is that copper in sulfides is primarily copper 1+, copper in water is copper 2+. And that oxidation, where oxidized copper species favor heavy bonds, that oxidation of copper 1+ to 2+ results in the signal that we see in the water. So we then said, let's test it. So we went to this remote area in Alaska and we collected water samples from springs and seeps and ponds like the one shown on the bottom left. And we focused on an area here where below the surface is the Pebble porphyry copper gold moly silver system. This is the world's largest porphyry deposit that is not yet mined. If it went into production, it would increase U.S. copper production by about 30% overnight, and it would rank as either the first, second, or third porphyry producing copper deposit in the world. So what you're looking at here are the symbols. All of the stars here, those are the water composition where waters were collected directly above the porphyry copper deposit, which sits beneath tens to more than 100 meters of exotic glacial till. So there's no sampling of the surface environment. There's no outcrop that would give you an indication of the presence of the Pebble deposit. The red, all of those are areas where we sampled waters, and their compositions isotopically tell us there's no copper sulfide in the subsurface. We then moved out and we were able to identify another already known epithermal copper gold deposit up here. And then using only the water compositions, we were able to identify 1, 2, 3 new targets, where this target, we could use the metal isotopic composition of water to predict what copper sulfide should be in the subsurface that the water reacted with. And the copper sulfides we predicted should be there, they've been pulled up by drill core. We then looked at hyper-arid terrain, so we went to Australia, the Northern Territories, and Queensland, and we did a similar exercise where there's a known copper deposit up here, and they have monitoring wells radially out from the known copper deposit, and they were curious as to whether or not the water compositions might help them doing brownfield or near known mine copper exploration. And what we were able to say is absolutely. The isotopic metal composition of the waters here, where these are salty brine groundwaters collected from tens to hundreds of meters below the surface, the metal isotopic composition of water indicates the presence of copper iron sulfides here. This has subsequently been drilled, and now it's a JORC-compliant copper resource. One of the things that I want to highlight on a chart here of delta 65 copper versus concentration is we're able to see the signal. In yellow is pyrite, in green is chalcopyrite, and the open triangles are not sulfide. These are copper isotope and copper compositions of water reacted with each of these three minerals. And so even at concentrations as low as tens of parts per trillion, we can detect the presence of copper sulfides and copper iron sulfides. So the wheel on the left is an indication of if there's a subsurface ore deposit and we collect water samples above it and then radially out, we can use the metal isotopic composition of the water within about 1.5 to 2 kilometers of the deposit to identify copper iron sulfide and copper sulfide mineralization. And then we went around the world and we sampled waters from every single one of these deposits, which include all of the other types of copper deposits that we currently mine copper from. Next year, I'll present more information on this one, but we also now figured out how to use plants and trees. So mesquite trees, which are very common in the American Southwest, they send roots down as deep as 65 meters or 200 feet. Those roots, they find groundwater. We have now analyzed mesquite trees by ashing them, and the metal isotopic composition of mesquite trees tells us what copper minerals exist in the subsurface, because the mesquite is sampling the water that chemically reacted with the sulfides. So last couple of slides here. On the left is a heap leaching operation in Arizona. About 20% of the world's copper comes from heap leaching, 80% from smelting. And heap leaching, it involves, as the video on the right shows, spraying what we call a lixiviant on top of a pile of disaggregated crushed ore. The lixiviant flows through the pile, chemically reacts with copper sulfide, copper iron sulfide, and copper oxide minerals. And then it's collected, and what we call the pregnant leach solution, that is then electrolytically refined and the copper is purified. Heap leach operations, one of the challenges with them is they are notoriously heterogeneous. So if you imagine a heap over here that could be tens to more than 100 meters high, and we look at a side view versus a plan view, in the side view, what you can see is that there are channels that allow for the preferential percolation downward of the lixiviant. What mining companies try to do is they want the lixiviant to percolate through the entire heap and react with all of the oxide and sulfide copper minerals they can come in contact with. So we started analyzing that pregnant leach solution. And what I'm showing here is that for a given heap leach operation, if we sample the pregnant leach solution at any time after leaching has begun, we can measure and use, as the y-axis indicates, the copper isotope composition of the pregnant leach solution to tell the mining company what copper minerals are being leached at that point in time. This is important because it allows the companies to modify the composition of the lixiviant that they spray on the top so that they can control pH, which is a huge factor in determining reactivity of the lixiviant with copper minerals. So we've done this now to monitor mineralogy in a heap leach operation. Just by measuring PLS, we can tell you you're leaching chalcocite. Just by measuring PLS, we can tell you you're leaching cubellite. We did work recently for one client where they thought they were leaching chalcocite, but we were able to use the metal isotope, in this case copper isotope composition of PLS, to tell them they were actually leaching cubellite and energite, not chalcocite. So they could change the composition of the lixiviant to increase the recovery of copper. And then the thing that's most hot off the presses for us is we've now figured out how to use the metal isotope composition of pregnant leach solutions to identify the formation of passivation layers. So the schematic on the left, the bottom is chalcopyrite. What happens during leaching is chalcopyrite will react with ferrous and ferric iron in the lixiviant. That drives oxidation of the copper iron sulfide or copper sulfide, which causes copper as a 1+ cation in the sulfide to be transported as a 2+ cation in the pregnant leach solution. Passivation layers commonly form and essentially create a shield around copper sulfide minerals in the heap that decreases the overall recovery of copper from the heap leaching operation. So we have figured out a way now to monitor and detect the presence of passivation layers, and not shown here, but I'll hit on next year probably, is the fact that we can now relate that to the pH, the acidity of the lixiviant, and mining companies that we've worked for have changed that composition so they can eliminate the formation of passivation layers. We've done a lot of work on environmental monitoring, And I'll put my last slide up, which is a couple of years ago, I started noticing a number of startup companies around the world claiming that they were going to do what mining companies can't. They were going to find new copper deposits. And after reading through all of the details of those companies, I realized they're just using the same data that mining companies are using, and they're less successful. So partners and I, we decided to set up a company because what we were able to do is demonstrate through academic, peer-reviewed scientific research, we figured out what a new signal is that none of the world's mining companies are using. And this signal is specific for specific minerals in the subsurface. So we're not guessing, we're not hypothesizing, we're not waiting until we drill. We can tell you, you've got chalcocite. We can tell you you've got supergene chalcocite versus hypogene chalcocite. We can tell you if you've got chalcopyrite. We can tell you if you've got chalcopyrite and chalcocite, and we can use a variety of isotopes to determine the relative proportion of supergene chalcocite to chalcopyrite. And so we set a company up, and the whole purpose of the company is to be a commercial lab to provide these services not only to the mining industry, but anybody around the world and anybody in the room who has an interest in having solid and liquid samples analyzed for pretty much every set of stable isotopes from lithium to uranium. We can do it. Thank you.